Sorry, mate? Yes, you will need to copy this down. So what we will do today is a very brief intro to polymers. We won't go into a huge amount of detail. It's really just as a bit of a precursor to this big topic that we're about to launch into. Okay? All right, what I happen to have in front of me is some examples of polymers. Okay? This is a polymer because it is plastic. Okay? So when you think of polymers, you think of plastic. So there's an example of a polymer just there. And my box tricks. Here's another piece of plastic. Okay, this is actually used for decking. I sort of borrowed it from. Borrowed it. Yeah, they was throwing this away. They had it sitting in a pile, and so what I've done is I've taken this stuff here that they use now for decking, right, in preference to wood. This is a polymer-based material. Okay, it's just all it is a plastic. It's a recycled form of plastic. But it's fairly strong, right? I've had cars sitting on top of that. It's a very strong plastic. These ones you would have seen before, okay? Yep, all right. So this one here is plastic, again, it's polyethylene, all right? These containers you've seen many times before, hopefully, okay? This one here is also polyethylene, all right? It's got the recycle symbol on it somewhere, all right? It's got a little recycle symbol, which means we can recycle that form of plastic quite readily. Here's another form of plastic, okay, from the ice cream that I was eating last night. What? This is the ice cream that I like, okay. So that one I was eating last night, or whenever I finished it off. And so this one also is a plastic, and it's also a little symbol in the middle, little triangle symbol with a number, okay? And if you do a little bit of research, that number tells you the sort of plastic that it is, okay, and whether it can be recycled and what it can be used for. This one here is actually categorised as a form of plastic, believe it or not. I've seen this before. It is, what is it? Foam. Yep, I had to break my esky in order to get hold of this. Wasn't very happy. So this is polystyrene. And although it doesn't look like a fibrous material, it actually is a polymer type material, okay? But of course you can't recycle this very well. Now we're not quite up to it yet, but in some of these plastics that I've got in front of us here, okay, this thing can go, you go that way? That way. In these plastics here, all right, all these things here, all right, should have got them up there, shouldn't I? Some of those plastics we can recycle and some we cannot, okay? We will not get into a lot of detail about this today, but further down the course we'll be talking about two groups of plastics, not the ones I'm talking about on the board here, not addition and condensation. We'll be talking about thermoset plastics, and we'll be talking about thermoplastics. So thermoset, thermoplastics. Thermoset plastics, set means it's set, it's locked in. Okay, this is an example of a thermoset plastic. If I put that in the oven, all it's going to do is to catch on fire and burn and turn into carbon. Okay, I cannot recycle this, all right, because it's actually got cross links. You can't see them. I can't see them from where I'm standing. All right, it's got cross links between all the polymer chains. Every time you cook, does anybody cook here? Like on the stove, the handles normally made out of a form of plastic. Unless they're a steel handle, of course, which don't conduct heat very much. The handles are called Bakelite, and Bakelite's been around since the early 50s when it was actually discovered, and that is a thermoset plastic. The old steering wheels on cars, the 70s and 80s, those big Bakelite steering wheels, the plastic steering wheels, okay, a form of plastic, all right? Not designed to break and not designed to be heated at all, all right? You can't recycle. Whereas, if I put hot water into this, or put it in the oven, it's just going to melt down to one puddle, okay, of plastic, all right, which I can obviously turn into small chips, and I can recycle it again into another container, all right, depending on the sort of plastic that it is. All right, so that's just very brief intro, because you're also sitting on plastic, not your bottom necessarily, all right? We know that's probably more like a triglyceride. because if it's anything like mine, it's probably fat. But I'm talking about the chair that you're sitting on. Okay, so the chair is made out of plastic, all right? And most things these days are made out of plastic. Laptop, plastic, okay? Bench top, plastic, okay? Floor, plastic, all right? So you'll come across them all the time. Pen lids, plastic, all right? Now, polymers. So essentially the word polymers, because you would have seen it before, poly means many. Hopefully, for those of you who've done a bit of, what's the word? Not, is it Latin? Greek. I don't know. One of the others, okay?
Greek.
I think is it Greek?
It's Greek.
We'll say it's Greek, all right? Poly means many, okay? And the second part of the word mer is short for monomer, mono one. So lots of ones at an end to end is what a polymer is, okay? Long chain molecules. So sitting up over here, okay, here's an example of a long chain molecule. I just carefully step over this illegally, okay? So this one has been here for a long time, all right? This one here is polyvinyl chloride, PVC. Here's the monomer, okay? The monomer is the single molecule used to build this polymer. Notice it's got a double bond, okay? What colour is white for our molecular building kits? It is hydrogen, yeah, and green is? Green is? Chlorine, okay? So we've got one chlorine, okay, 3 hydrogens and a double bond carbon. This adds end to end to form PVC. All the stuff that we've got our switches made out of, the gutters, the pipes, PVC, PVC glue you can get as well, okay, in liquid form. Now, I didn't get enough, I didn't have enough of these to make, but you know, in theory, to get a molecular weight greater than 10,000, I would have had to take this like through to the physics lab, and Mr. Elliott wouldn't have liked that, not having molecules hanging in the physics lab. Okay? So, this is the sort of size of molecule that you need to think of when we think of polymers. So prior to this, what was the biggest molecule you would have seen in this course? No. In the organic section, what's the biggest molecule that you've seen? It would be protein, yes. Proteins are very large structures, or what was the other larger molecule that we would have seen? The fats and oils, yeah. Fats and oils, we haven't done soap yet, but if we had of, we would have included soap in that list. So proteins are large molecules, we know that already, okay? Triglycerides, fats, oils, soaps, pretty large molecules. All right, repeating unit. So the point about all polymers is we can identify a repeating unit. And I put there, it's not equal to a protein. Because what's the repeating unit in a protein? Is it a repeating unit? It's not, okay? What's unique for me, okay, and it's unique for you, we've all got different proteins, we've all got a different genetic base, depending on what cells we obtained from our father and what we got from our mother, okay? It's all different. There's no two genetic characteristics that are the same. Certain parts of that gene, okay, we can identify though with certain characteristics, you know, like say tallness or shortness or, in my case, smartness, right? Or baldness is probably a better one, all right? So unfortunately, I got the bald gene, all right? So the point I'm trying to make here though is that a protein, although it looks like it's got a repeating unit, actually it doesn't. We talk about a sequence of genes, okay? And that's what we can talk about, okay, within a protein structure. So it's not as if we've got one thing repeated many times. We've got 20 amino acids, okay, that can be repeated randomly over the length of the chain. We call that the primary structure. All right, addition polymers. Addition implies adding, okay, adding. We're adding one monomer to another, to another, to another. The key here though, and it's not done in the book very much, the key is we normally start off with a multiple bond in the structure. So we'll do polyvinyl chloride. So I'm going to look at the monomer, okay, for polyvinyl chloride, and this is the monomer for polyvinyl chloride. It's called vinyl chloride, okay? So this is the monomer. I'm going to put this alongside because we'll draw the polymer for this in a minute, and I want to relate that to what we call the repeating unit. So we put this alongside, keep on going, try and keep it nice and neat, all right, as we go. Because I'm not in a hurry, I can pretend that I'm in the middle of an exam and I'm very relaxed and not panicking about anything, and so on. All right, so these are my monomers, and what's not talked about a lot is what turns a monomer into a polymer. Okay, has anybody done fiberglassing before? So you've never mixed up fiberglass and put it onto a boat or onto a surfboard, or no? No? All right. So typically also, like just in normal repairs for cars, sometimes I use fiberglass in place of metal and lead, right? Because it's cheaper. It doesn't last very long though, right? Once it gets a bit of rust in it. Anyway, so this is the beginning of our polymer, but it's only got a single monomer. We have to have something, I'm going to call it in this instance a radical, to start the chain or start the addition process off. Now it gets a bit complex. So a radical, if you think about it in the context of, say, fiberglass, okay, if you're working with fiberglass, you have typically a can of liquid, which is the fiberglass liquid, and you have a little dropper bottle of what we call the hardener. Okay? So when you are ready to start fiberglassing, you take some of the main liquid out, mixed up into a cup. Okay? You get a small quantity of the hardener, you put the hardener into the actual fiberglass liquid itself, you mix it up, and from the time you mix it up, it begins to form a polymer chain. Okay? Watch this one. Oh, is that more important than me? Sit down, right? So the polymer chain, okay, is what actually happens. Okay? Where's mine? Alright, now, so we've got this radical that starts the process off. Notice it's only got one electron there by itself, just one, okay? So I'm going to just use a single-headed arrow to show you that this is actually trying to form a bond, okay? That's what it's doing. This double bond here, one of the electrons breaks, okay? One of the double breaks, and it goes and bonds with the radical that I'll show you in a minute. We'll draw this structure underneath in a minute. And the other electron forms the other side. So the first step in a sequence of many steps is we get this. So we get this structure here formed. There it is there. And we get a single electron. Just formed basically a bigger radical molecule. Okay? Keeps on going. So then this monomer comes along, get the right colour, this monomer comes along, it donates just one of its electrons in the double bond, and we get a chain reaction set up, okay? It's not like a chain reaction as in like a nuclear explosion at all, right? Because there's no energy released here. It's just simply all these monomers adding end to end. And the longer we allow it to go for, and the slower we allow that process to occur, the longer the carbon chains. So one thing to think about is that if I were to put lots and lots of radical in with my monomer, can you work out what might happen? It's a bit beyond what we're doing at the moment, but what do you think is going to happen if I put lots of radicals in? No, it's going to be a huge chain. I'm going to get lots and lots of chains that are very short, because they won't have the opportunity to build end to end with themselves. Another radical is going to come on here and go bang, and I've got a chain that's too long, as in 2 carbons long. Okay? How do you think that would affect the properties of a compound with short chains? Weaker. It's going to be pretty weak and very brittle. Okay, so we can make compounds like that, and we can also make compounds that last forever, because we know we can build cars out of plastic. That means motors bodywork, everything can be made out of plastic now. And all it is what sort of the monomer am I working from, okay? And how long do I want the chains to be? And the other thing is, do I want it to be a thermoset polymer as well? Do I need to have something that's going to cross-link the chains? Alright, so enough of that. So that's just going to keep on going. I'm just trying to exaggerate what's happening there. And this keeps on going. Get a chlorine there. I'm just going to try and, when you're doing polymer structures, and you will get 1 or 2 to do in the exam, not our trial, but the end, try and keep them aligned underneath one another, okay? It makes it very simple, all right, when you're trying to work out what's happening in the structures. If you get them out of alignment, you get really confused. Now, it doesn't matter if you draw one bond a bit longer to get them sort of in order, no big deal, okay, provided you've got it in the right spot. And we keep on going. So this is my structure for a polymer, and that'll keep on going indefinitely. But when we're doing structures for any polymer, the hardest thing to do, or one of the hardest things to do, is not just drawing it, but picking out the repeating unit. Because we don't draw a polymer like that, okay, in our textbook or in our questions. We draw the repeating unit, and we put an N on the end of it. So we start anywhere, it doesn't matter where you start, okay. I'm trying to work out what the monomer is. So I'm going to start here, got carbon, HCl, and I've got carbon and a HCl. You can obviously see hopefully that it repeats itself. This is a simple addition polymer. We get more complex. Bracket N. So that's the repeating unit for this polymer, for our polyvinyl chloride. We don't need to repeat or draw all those. Typically what you're normally given in a question is they give you the polymer, as you'll see in the essentials there, and they say pick out the repeating unit. Okay? And then from the repeating unit, go backwards, give me the structure for the monomer. That's how we tend to do it, okay, in the book. So far, so good. Alright, condensation polymer. Oh, before I do that, sorry, I forgot to mention that for an addition polymer, they really just look like this. It's just like A, and A is just for addition. It's just a monomer added end to end. It's the same repeating unit over and over again. Square bracket, okay, N. That's all it means, right? To simplify it as much as what I can. Alright, a condensation polymer is or has got 2 or more monomers. And I think the best way to look at a condensation polymer is to draw one. Okay? So what I'm going to do is just one type of condensation polymer. There are 2 groups that we're going to look at. We're going to do polyesters and polyamides. My shirt's probably got made out of polyester. If I take it off, which I probably don't want to do right now. Look at the label, okay, and you'll probably see somewhere on the labels of these things that a certain, oops, here it is, yep, look at that. 100% polyester, okay, on my label, all right? So this is an example, that is the outside of this jacket, probably everything else that matter, is made out of a polymer, okay, 100%. It's also made in China. All right, so polyester. If we're going to look at a polyester, all right, the assumption for these is that they are bifunctional, which means we have 2 functional groups in the structure. All right, so I'm going to do one of them. I'm going to do the structure for nylon first. Nylon is a polyamide, and it looks like this. So nylon, oops, there, CH2, 6NH2. That's one of the monomers for nylon. And if we were allowed to do this, okay, I would have a beaker set up, and just imagine this, actually might look it up on YouTube in a minute, and I used to be able to get, but we can't get anymore, the 2 monomers that form nylon. I'd have a beaker, I'd pour the 2 monomers, one in first, one in the second, then I'd get tweezers, then I could actually pick out from the layer where they contact the 2 monomers, and I could actually just draw out a thread of nylon like that and keep on going, keep on going, keep going, all right? I don't know if we've got the video in sector, but I might have put it in there. So this is one of the monomers for nylon. The other monomer looks like this, and I'm going to draw it properly, that would be better. This one here, CH2, 4, O, and H. So we've got a a molecule that's got two amine groups in it and a molecule that's got two carboxylic acid groups in it. And I'm going to do another one. So the amine I'll put over here, CH2, 6, NH2, and so on. Alright? And I've put these such that the amine is next to the carboxylic acid. Now going right back to what we did in the organic section, if I react a carboxylic acid with an amine, what do I get? An amide. Okay, that's what we get. So we end up with this. And I'll just change the structure slightly. So we're going to end up with this compound. There it is. Okay. And we'll keep on going because I want to try and get that C double bond O underneath that C double bond O of my carboxylic acid. And I just keep on going. That's the rest of that carboxylic acid. And then it's going to do the same thing over here. I'll try and keep that nitrogen underneath that one. Okay, and then I've got CH2, 6, NH, and dot, dot, dot. It's going to keep on going. Now, here's where it gets a little bit more complex again. I think I've used that word about 20 times, right, in the last 20 minutes. So this is a polyamide, all right? It's also called a condensation polymer. Any ideas why it's called a condensation polymer? Water's formed. Who said that? Thank you. Thank you, Will and Jack. All right. The other byproduct of this, each time we do that, is we form water. Okay? Every link that we form in the chain, we form water. That's where the word condensation comes from. So the two monomers come together, they form a link. In this case, it's an amide link, and they spit water out. Okay, not actually like that, but water's produced in the reaction. All right. Now, for a condensation polymer, the things you have to be able to identify is what sort of condensation polymer is it. So there's only two of them. There's this stuff, polyester, but you have to identify it from the structure, of course. All right, and there's polyamides. So the first thing you tend to do is to try and identify the link in the chain, because there's an amide link. And here is an amide link. There it is there. Okay? So the amide link is reasonably straightforward to identify, I hope. Alright, so obviously I categorise that one as polyamide. Alright? Now, not only are we asked, or will be asked to identify the link, and say what sort of a polymer it is, they'll say, okay, so what are the two monomers that we use for this condensation polymer? Jack? No, but I'm pleased you raised that one. When we did this in this section on proteins, we called this polypeptide, didn't we? A polypeptide, when I think we did that, I said it's a polyamide, that's what it is. But we don't use the word polyamide because a polypeptide is a naturally occurring polyamide. So they call it a polypeptide. So when we're talking about proteins and enzymes in that area, they're called peptides. In this case here, nylon, whether it's synthetic nylon or natural nylon, it is a synthetic polymer called a polyamide. But you don't call a protein a polyamide, because it's made from amino acids, peptides, okay? Make sense? All right, where do we get to? Oh, the repeating units, all right? The repeating unit in the structure. So again, there's no rules about where you start, but I try and work from the left all the time, and then I work my way across to the right. Seems logical. So I'll start there, and I'm trying to find an NH next to a CH2-6, because whenever that starts, again, that's my repeating unit. So keep on going, we'll go from here, NH, no, because it goes C double bond O, no, no, and here's where the NH-CH2-6 occurs again. Okay, this will take practice. Once you've done it for about 35 years, it's pretty simple. There, and N. So there is my repeating unit. That's only one option, because I could have started here. It doesn't really matter where I start, provided I've got enough of the molecule drawn to get to the end of my repeating unit, yeah? So that could be done easily. And of course, the next thing that would be asked is, what are the monomers? So then we have to then break. We break it at the amide, just like we would have done, okay, in our previous section organic. And then we know that the NH would have come from an amine, so we put the NH2 there. The C double bond O would have come from a carboxylic acid, so we put the OH there. Now obviously I've gone in both directions. I've given you the monomers, built the polymer, and then broken the polymer apart back into the monomers. But you don't get all that in a question. Alright, you'll either get that and you'll be asked to draw the polymer, or you'll get that and asked to work out what the monomers are and identify the links in the chain. Okay, it's about as far as what you would need to do. Alright, what else was I thinking? That's all I was thinking. Alright. Oh, the other thing was this. So this one here, if I were to represent the two monomers like this, let's assume this is monomer A and that's monomer B. When we do this, it looks like A, okay, C, B, C, A, C, B, C. Okay, and you can see that it goes A, B, A, B. Okay, and of course, what's the C in this case? It's the, no, it's the link. Okay, so the A and the B are the two monomers, and the C is the link. In this case here, the link that I've chosen is this one, an amide link. Okay, but we didn't get there. We will next session. We could also have this link here, which is, get that one right, that would be an ester link. In that case, it would be polyester. But we haven't got polyesters today. All right. Like I didn't have D. The ACDC, ACDC. Wouldn't it? Should have done that. All right. Questions? Any questions about that? So we'll pick this up again in the next few lessons. All right. That's really as far as we need to look at, and you're going to grab some exams and start revising straight away.